Okay, so we've been presented with a hydrocarbon, and we've been told that the empirical formula of this hydrocarbon has a formula of CH3, right? And a molar mass of, well, the molecule in general has a molar mass of 120 grams per mole. And so we've been tasked with trying to figure out, well, what's the molecular formula? Okay, so how would I approach this? Now, I would give consideration to the fact that we have been provided the molar mass of the molecule. We haven't been provided with the molar mass of the actual empirical formula. Why this is relevant is that if I was trying to solve this, I would want to compare the molar mass of the empirical formula with the molar mass of the molecular formula, and that would give me an indication of how to work out the molecular formula, right? Now, the molecular formula in this case would be in relation to the empirical formula. Well, we know that the empirical formula is effectively the smallest, or in some would say the simplest, whole number ratio of the atoms of each element present in the compound, or and the molecular formula is the actual number of atoms of each element present. So there can be differences between the two, assuming that the molecular formula is not also the empirical formula. So one of the first things I'm going to do, based on that rationale, is I'm going to try and work out, well, what's the molar mass of the empirical formula? And to work that out, I'm going to need to effectively get the molar masses of the constituent elements, which in this case is carbon and hydrogen. And in order to get that, I'm going to refer to, well, you might already know what the relative atomic masses of those are, just generally based on how common these elements are. But I'm going to refer to the periodic table and just articulate my reasoning. So, okay, so as I said, we've got carbon and we've got hydrogen. Now, the relative atomic mass of carbon, as you can see here, is 12. The relative atomic mass of hydrogen, as you can see here, is 1. Now, these, in this particular case, this is effectively the molar masses as well. So we can say that the molar mass of carbon is 12, right? 12.0. And that the molar mass of hydrogen is 1.0, okay? Now we're going to use these values to work out the molar mass of the actual empirical formula. So let's just do this. So you may remember the formula with regards to working out the molar mass, right? So it's basically the sum of the the molar mass of each element present multiplied by the number of times it occurs in the formula, and then the sum of that. So effectively, I'm not going to write out that formula, but for this particular question, that would be 12, which is for carbon, multiplied by, okay, how many times does carbon occur? Well, here it occurs once, right? So, and add that to the for hydrogen. So hydrogen has the molar mass of 1. Multiply that by, well, how many times does hydrogen occur? As you can see, the coefficient, the numerical coefficient associated is 3, so we're going to do 3. And so that's going to give us what value? Well, if you work that out, you find that that gives you 15, okay? So that's going to be 15 grams per mole, okay? Or should I say, like, the MR, right? Like I said, the MR of CH3 is going to be 15 grams per mole, right? Right? So, moving forwards from that, what I'm also going to do is, we need to work out what the multiplier is, right? Because obviously this 15 is not the same as 120. So we know that for the actual molecular formula, it has a greater molar mass than the empirical formula, but we need to work out exactly how different it is. What's the actual comparison? And we'll do this by determining the multiplier. So what formula am I going to rely on for determining the multiplier? Well, the formula I'm going to depend on here is actually, okay, so multiplier, let me just get rid of this. I don't know how. Multiplier is equal to, and I'm going to abbreviate this slightly, but it's effectively the molar mass of the molecular formula, right? So the MR of the molecular formula divided by the MR of the empirical formula, okay? So that's molecular formula, empirical formula. So we have actually, in our question, we've been told that the molecule is actually 120 grams per mole in terms of its, what would effectively be the molar mass of the molecular formula. And we've already here worked out what the molar mass of the empirical formula is. So we just need to really plug in these values. So it's going to be 120 divided by 15. Okay, so let's do that. It's going to be 120 divided by 15. And so I invite you to have a go, work that out to see what you get. Now, if you do that, what you should find is you get 8. Okay, so the multiplier in this case is actually going to be 8x, right? So the multiplier is equal to 8x. And now applying this multiplier that we've determined to the empirical formula, let's start with the carbon, right? So for carbon, we're going to have effectively, we started with a 1, right? So 1 was effectively, I mean, it's not, we've not got a written 1 there, but we know that the carbon is just a C with nothing next to it. So we know the coefficient is 1, it's implied, right? So 1 multiplied by 8 is equal to 8, right? So therefore we can, from that we can deduce, okay, well, for carbon it's actually going to be C8, right, in the molecular formula. And if we do the same for hydrogen, we remember it was CH3, right? So it's CH3. So the actual coefficient associated with the hydrogen, right, is 3. So we need to do, it's going to be 3 times 8 this time for hydrogen. 3 times 8, and that's going to be, or if you work that out, what you should find is that's 24, right? Okay, and what that tells us is that in the actual formula, we're going to get H24, okay? And so if we consolidate those values and we put that together, we get a molecular formula of C8H24. Okay, so in this particular case, our molecular formula is actually C8H24. Now, before I proceed, actually, even though we've determined our molecular formula for this question, this in particular, if we look at this molecule, it is a very, very, very strange molecule. C8H24, right? So for example, for even I mean, there's a lot of molecules you can try and imagine compare even alkanes, right? For alkanes, you would not expect such a high number of hydrogens associated with the carbon, right? But in this case, you've got 24. This is what you could maybe describe as more of a theoretical molecule as opposed to an actual molecule. And if it did exist, it would very, very, very likely be extremely, extremely, extremely unstable. there may well be theoretical condition, or some extreme conditions under which it may exist, but if you refer to something such as a valency of carbon, you'd find some suggestions as to why, even if it did exist under certain conditions, why it might likely be quite unstable, right? Okay, now one of the other things before I conclude this is if we consider this molecule. This is a different molecule to the one we've just determined, the molecular formula, etc. But some of the principles at play in this, that concerns this molecule, actually give some food for thought as to the plausibility of something like C8 H24. What we have here is a molecule that's called methanium. Okay, so this was first prepared, at least as far as what's documented, it was first prepared in 1950 in Russia, right? So it's prepared by a Russian scientist and his assistant, and this molecule is very unstable. It's very reactive. If you think about the valency of carbon, it's usually 4. But here, this is a situation where carbon has kind of managed to get a level of association with basically 5 hydrogens, right? So it's not the most stable molecule, which, I mean, that's an understatement. But I would invite you to have a look at looking into methanium, how it somehow manages to form 5 bonds when, based on what we know about carbon, maybe it is quite unusual, but in this case it is something that is actually possible under certain conditions. So it's an interesting thing to look into. But yeah, anyway, in our case, our molecular formula is C8H24. Okay, all right.